things are all going fine. We are glad that you could join us today for these lecture series. This is the second lecture of many that we have planned as a part of the outreach team of the Education and Public Outreach, or the EPO team of LIGO India. The first lecture was by Professor Sanjit Mitra on Wednesday. There will be the next lecture on Monday, and we have a few more lectures lined up as well. At this point, I should also request join us today for these lecture series from you. This is the second lecture of feedback form as a part of the description of this video later, and we request that all of you please fill up that feedback form. Tell us what you liked about these lectures, things which you did not like. What else would you like to see? Would you like to have more general public talks, or would you like to have more detailed technical talks as if they were lectures in a college? So all of these questions we would like to hear from you. We will try to accommodate as many requests as possible. Also, throughout the talk, you are free to ask questions at any point. We will, if there are any urgent questions, we will take them up at that moment, and I will try to answer them immediately. Else, I will talk for about 45 minutes or so, and we will take those questions in the end. Now, before I start the talk, I would also like to express gratitude to the entire LIGO India Education and Public Outreach team. In particular, Samir, Vaibhav, and Ankit have been doing a lot of behind the scenes work to make this possible. We are also getting help from Gaurav today in reading all of your questions, collating them, and passing them on to me. With that, let us move on to my topic of the day, which is seeing what we hear, electromagnetic counterparts to gravitational wave sources. So when you think of astrophysics, this is probably closer to the image that comes to your mind. The video that you are seeing here right now is a time lapse of our telescope, the Growth India 70 centimeter telescope at Hanle in Ladakh on a mountain called Dibka Rasta Re. This video them was and taken during commissioning of the telescope. With that, let us move on to my topic. Lecture is really focusing on gravitational waves, which is completely a different type of waves. Electromagnetic radiation in itself encompasses things like X-rays, gamma rays, radio waves, ultraviolet light. The video that you are seeing here right now is a time, but gravitational waves are not among those at all. If you have not got a primer on gravitational waves, I would strongly encourage going back to Sanjit Mitra's talk and looking at the video that we have shared online. But as a very quick introduction to gravitational waves, you have all probably seen this analogy where you have when a heavy mass is placed on top of a surface, then the surface bends. Of course, space is 3D. This is just a rendering shown in 2 dimensions. And you could imagine that when two objects like this have distorted space around them, if the objects start moving around each other, then the distortions in space are going to move around with those objects. In principle, in practice, this means that they are going to create ripples in effect, which are going to spread out from the source and they will spread out through the universe. Okay, so these ripples are nothing but gravitational waves. These waves are detected by using these very, very, very sensitive instruments. So sensitive, in fact, that Albert Einstein around them, when he predicted if the objects start moving around each other, then the distortions in them to be ever detected. So what we have here is at what you see here is what is called the center station of LIGO Livingston, and you have these two long pipes stretching out perpendicular to each other. The pipes are 4 kilometers in length, and this is also what LIGO India is going to be like. And through these pipes, we have laser beams which are being reflected from mirrors, which is this is one of the end stations. So a laser beam is actually getting reflected from one of these end stations, coming back to the center. A different laser beam is going to the other end station and getting reflected. And these allow us to monitor the lengths of these beams very accurately, of these two tubes very accurately. And based on any differential expansion or contraction of those pipes, we can actually detect gravitational waves. There's, of course, a lot of data processing that goes in there. The collaboration is a very large collaboration, more than 1,000 people working on many, many aspects of it, ranging all the way from data scientists, physicists, optics engineers, civil engineers, mechanical engineers, you name it, computer scientists, everybody is working on this. And what they have done so far is here is a large range of black holes that have been detected by the advanced gravitational wave networks. This includes the two LIGO detectors in the US and the Virgo detector in Italy. Soon coming online is the Kagra detector in Japan. The animation that you see here shows two black holes orbiting around each other. As they orbit, they come closer and closer to each other because they are losing energy, and at one point they merge and become a single black hole. But as I said, I'm an astrophysicist at IIT Bombay. What I like to do is I like to observe things. So suppose I take a telescope and I point it to one of these sets of black holes as they are merging. Here is what I will see. Nope, that is not a video glitch. Your screen has not gone blank. I will not see anything because black holes got the name because they're black. The gravitational field is so strong that not even light escapes from them. And if that is the scenario, then we don't expect to see anything with conventional telescopes from black holes. But we want light. So, what gravitational waves detect are changes in gravity or gravitational waves. They are not exactly changes in gravity, it's more subtle than that. But they are detecting gravitational waves which are coming from the masses of the object. So, they are actually telling you about the masses of the components, they are telling you about the orbits of the two objects involved, and so on. On the other hand, if we saw light of any sort, if we saw electromagnetic radiation, then that is going to tell us about surface phenomena. It's going to tell us about whether what material was ejected, whether jets were launched, what kind of elements were present when that merger happened. Again, all of these won't necessarily be seen from black holes, but those are not the only types of sources. We will come back to that in a little bit. Okay, but for now, let us look at the astrophysics aspect of it again. So I'm an astronomer, and for any scientist, if you are really pursuing any question, then what you would ask is, what is it that keeps you up at night? For an astronomer, the answer is everything. We observe at night, so everything keeps us up. But we have two questions in particular that my group here works on addressing. Question one is, where are all the heavy metals in the universe formed? And the second question is, what is the equation of state of ultra-dense matter? So let's explore these questions in a little bit more detail. Okay, so here is a periodic table of elements. I'm sure you have seen some form of this at some place, but this particular periodic table is color coded in a lot of different colors. And in those colors, you have hydrogen in the upper left here and helium in the upper right here. And these were primarily made in the Big Bang itself. But then you have all of these elements here, the carbon, nitrogen, and oxygen, which are the basic elements that make life possible on Earth. You can see that all the oxygen on Earth, almost all the oxygen in the universe actually, was made from exploding massive stars. On the other hand, most of the nitrogen that we have here, the atmosphere is 70% nitrogen, or the carbon, that is the vital molecule for life, vital atom, vital element for life, was largely synthesized in dying low mass stars. And then I want to draw your attention to all these purple blocks at the bottom. This includes some elements which some of you might be fond of. For example, here is silver, there is gold, there is platinum, and so on. So where were all of these formed? These were formed in merging neutron stars. So merging black holes are not the only type of signals that LIGO detects. It can also detect the mergers of neutron stars. So let's look at how to manufacture gold. Okay, this is a quick course called Gold Making 101 for you. So what you do is you first start with a universe that is primarily hydrogen. You form these huge, massive stars of hydrogen, and in those you start nuclear fusion and you start creating metals. Now, metals here is as counted by astronomers. If we have hydrogen, we have helium. If there is anything above that, we just call it a metal. That is, of course, not what the formal chemistry definition is, but that is the astronomers' way of referring to things. So we now have these massive stars, and at the end of their life, they explode as supernovae, and all of these metals get spread around throughout the universe. Once these metals are spread around, then from these ashes, we create a second generation of stars. And then we again blow up these stars. Some of them explode as supernovae, and they then create neutron stars. Okay, as explosions, of course, some stars will have other kinds of death. Some supernova explosions may create black holes, but some types of stars will now create neutron stars. So let's just keep track of things here. We have taken this material. We have created stars, killed them, created a second generation of stars. We have killed them too. So 2 killings. But are we done yet? No, we are not. So now what we want to do is we want to take 2 of these neutron stars together, make them orbit around each other and merge. Of course, we can't literally set it up, but the universe sets it up for us. And then when those 2 neutron stars collide, they are going to create a black hole. And as a side effect of this third killing, we are really creating some gold as a side effect in that debris, right? So we have 3 iterations of stars being formed and killed, and that is what is giving us the gold in the universe. On the other hand, let's look at the equation of state of matter. Some of you may have seen something called the phase diagram of water. So what is shown here is different lines as a function of atmospheric pressure and temperature. If you are in a certain region here, for example, if you are sitting in this side at very high temperatures or low pressures, you have vapor. At very low temperatures, you have solid water known as ice. And then this is where you'll find liquid water. There's something called a triple point. Even if you have not heard this in a technical way, if you have used a pressure cooker, then you're familiar with this. If you increase the pressure, then the boiling point of water goes up, which means that the water inside the pressure cooker gets hotter, and that means that you can cook food more easily. Okay, so all of this, broadly speaking, is called the equation of state. The equation of state is nothing but a relation between the pressure and the density of a medium as a function of temperature. So equation of state for water and for other metals and so on is all well and good. But what happens at the most extreme conditions in the universe? What if you have matter which is so dense that the density is heavier or higher than even the core of an atom? Neutron stars are one such place. The density at the core of the neutron star is a factor of 2 or 3 higher than atomic densities. If you take a spoonful of neutron star matter, that will weigh about as much as Mount Everest. That's the density we are talking about. And we want to understand what really happens to matter in the most extreme conditions like that. So, can you actually do any experiments for this? Well, since we are talking about atoms here, the conventional way to do that would have been to actually go to a particle accelerator. So you collide particles together and you watch the aftermath. You see what happens. These colliding at high energies create other particles, subatomic particles, and so on. That is not quite interesting enough. So you say, okay, let's collide bunches of particles together. This is the kind of stuff that happens in, say, the Large Hadron Collider. But come on, we are talking about astrophysics, most extreme scenarios. 2 slides ago, I showed you a picture of Rajnikant. So clearly, bunches of particles are not going to be enough for me. So how about you take 3,000, lots of thousands particles, about 3 into 10 raised to 57 particles, and collide them together. And that is what nature does, the universe does for us naturally when you have neutron stars which are colliding. So here's an artist's rendering. It is technically quite accurate. The blue things are representative gravitational waves. You wouldn't actually see them. But the 2 neutron stars orbiting each other collide, and there is a massive explosion that launches jets. It throws around all of this matter escaping from the neutron star. The jet hits circumstellar medium, slows down, and this is huge. We are talking about lots and lots of energies. More energy was emitted here than the sun would emit over millions of years. And all of this was emitted within a fraction of a second. So these kind of mergers is what would actually be these most extreme particle accelerators in the universe that you could think of. And one such case where this really happened was an event called GW170817. Okay, so this simply stands for gravitational wave effect on the gravitational wave event on the 17th of August 2017. So if there were an event that happened today, it would have been called GW2003, 04 for the month and 03 for the date. So GW170817 was detected by LIGO. It was the first time that gravitational waves from binary neutron stars were detected, merging neutron stars. The LIGO signal is shown in this panel at the bottom. The x-axis is time going from minus 10 seconds to plus 6 seconds. And this little yellow-green trace that you see is what is called a chirp. It is this frequency of the neutron stars spinning in around each other. Note that the frequency at the peak is more than 300 hertz. That is way faster than even the wheels of, say, a F1 car. And you are talking about two stars which are both more massive than the sun, going around each other 300 or more times every second. And just about 1.7 seconds after this event was detected, we saw a burst of gamma rays, which was detected by two satellites. One is called Fermi, and two different energy ranges from Fermi are shown here. And another satellite called Integral also detected this burst. Now, when I say this event happened on 17th of August 2017, what I mean is that we detected it on 17th of August 2017. The event itself is very, very old. It was 130 million years ago, but the event is 130 million light years away. So we didn't even have humans on Earth when this happened. And light has been traveling for so long, and it reached us about 2.5 years ago. And this, of course, was a big deal. And we have an Indian space telescope called AstroSat, which is very sensitive in X-rays and gamma rays. AstroSat has detected thousands of such explosions in space, not directly related to this, though, but a different kind of explosions. Sorry, I didn't say thousand, did I? Hundreds of such explosions called gamma ray bursts, which are explosions of massive stars. And we were quite sure that if some other satellites have seen this, then AstroSat will also have seen an event here. However, unfortunately, when we looked at AstroSat data, we saw absolutely nothing. And the reason why we saw nothing is actually shown here. But before I go to that, there's a question from Rohit Chinswadkar asking, why is time shown negative here? Well, instead of showing time in arbitrary units, what we have simply done is t equal to 0 has been selected at the time when the merger actually happened. So the x-axis really is time with respect to when the merger happened. So moving back here, what happened actually was this dark green oval that you see here is the region where LIGO and Virgo together said the event must have been located on the sky. Gravitational wave detectors cannot triangulate the location of a source very well. Okay, for instance, it is more like when you hear the sound of an airplane, you can say that, oh, it came from somewhere there in the sky, but you cannot exactly point to that location. You still have to look there, search around, and your eyes are what help you narrow that down. Similarly, LIGO and Virgo together, first, just the two LIGO detectors gave this large green oval plus this region here, and then the event localized was here. But then you see this gray circle over here, and this gray circle was the region that was hidden behind Earth as seen by AstroSat at the time of the event. So basically, we missed the event by about 300 seconds, 5 minutes. Okay. So the Earth, suppose this is the Earth, AstroSat was here, and the event happened on this side, so that AstroSat couldn't see it. Unfortunate, but well, that was not the only telescope that we have. One of the first telescopes to follow this up. This event actually happened in evening in Indian time, so it was just around time of sunset. So we immediately swung into action. The HCT, or the Himalayan Chandra telescope, is a 2-meter telescope. It's located at the same site, quite close to the telescope I showed you at the start of this lecture in the first video. This was one of the first telescopes on the sky, but at this point, one of the LIGO detectors had still got some data processing to do. So they could not localize the source well on the sky at all. The source was pretty much anywhere. So what we did is that we pointed at the centers of some of these gray locations marked here, which is where neutrinos had been seen. But the final event localization was here. So unfortunately, although we were ready to point, data analysis from the gravitational wave community had not been completed enough to tell us where to point. And that is why we couldn't possibly cover the entire area. We just had to observe these locations, and we missed the actual detection itself. But we were not the only telescope in the world. There was a huge frenzy of observations that went on. So here's an animation made by one of my students and some of our collaborators abroad. What it shows you is red shows optical and infrared telescope. Green squares show you radio telescopes. For instance, you can see the GMRT, Giant Meter Wave Radio Telescope here. The event was in the southern sky, so you can see most of the follow-up actually happened in the southern hemisphere. And you can see there's a large number of ground-based facilities that are following this up. Especially, you can see that the optical and infrared facilities go into action when the dot becomes big. That is when they are taking data, and they have to go into action right after sunset. Radio telescopes, on the other hand, can happily observe throughout the day as well. So as we go further and further away from the event, we are now almost 2 months since the event, 1.5 months since the event, and observations were still going on. Lots of data was acquired. The final paper, in science, when you make a new discovery, you convey it to all of your colleagues by having what is called a refereed journal paper. So the final paper that was published on this included data from more than 100 different instruments, 3,500 or more scientists from more than 1,000 different institutes collaborated together to make this possible. This is the discovery image itself. When optical telescopes swung into action and observed the entire green oval, they found this. So this large blob that you see here is a galaxy. The lower image is of the same region, but if you compare the two images, you see that there's a black dot over here, which is new, which is not seen in the older image. And this was a new source which was not present early on, and that is how people said, oh, this must actually be optical emission from that merger. And we will come back to this in a little bit as to how did we know that this is not some new random source. Okay, and this is not the pretty image that you imagined, but not all of astronomy is pretty pictures. Here are the first 6 observatories that actually imaged this source. And you can see the image quality is very, very different for each of them. You can see there's a lot of noise here. This image from master, for example, visually looking at it, you probably might not even be able to realize that there is a source here, but when you do advanced data processing on this, then this little dot which is seen in all of these images really does show up. No Astro Talk is complete without pretty pictures. So here's a Hubble Space Telescope image of the same galaxy. This image was taken before the event happened, so again the source is missing. But you can see these 3 circles here, which is an image in ultraviolet light, an image in infrared light, and an image in radio, which actually show you the source being detected across all bands of the electromagnetic spectrum. So here is an image taken by GMRT. The left 2 panels here, this one and this one. These 2 panels are actually showing you data from GMRT. For those of you who don't know, GMRT stands for Giant Meter Wave Radio Telescope. It is the world's largest low frequency radio telescope, and it's located right here in India. It is located close to a town called Narayangaon, which is roughly halfway between Pune and Nashik. So you can look it up, and in fact they also have public tours every now and then. So when the lockdown ends and you start going around again, you should plan a visit if you have not been there. Here is more radio data. GMRT data was an integral part of this, working again with radio telescopes from all over the world, trying to understand what is going on. But as I said, seeing a new source in the sky doesn't necessarily mean you have found something. So there are really 3 different things that we are talking about here. First is that there was a gravitational wave event detected by LIGO and Virgo detectors. Second is that there was a high energy trigger, some kind of burst detected by 2 of the space telescopes. It was missed by several others like AstroSat, Swift, Calet, and so on, which detect a lot of these explosions in the sky. And then there is something that we call the afterglow, which is the optical infrared radio source, which was seen by various telescopes, and you saw some images of that. But what we really had to do was we had to work hard to prove that these 3 seemingly different things were indeed related to each other. And that is only after we have proven that can we actually put together all the data to interpret what it is that happened in the sky there. So how do we know this? So first, let us start by comparing gravitational waves with high energy telescopes. So the argument there is made on the basis of 2 things. First is, what are the odds that you will see these events right next to each other in time? So we had, of course, discussed, by we, I mean the global scientific community had discussed these kind of questions before, and we had decided that if there is X-ray emission from such an event, then based on various theoretical models, it should be within, say, 100 seconds or so of the gravitational wave event. Now, there are 86,400 seconds in a day, and there is on an average one such gamma ray burst per day, which means that the odds of something coinciding are about 1 in 1,000 or so. Okay, that's good. 1 in 1,000 makes it unlikely that this is a chance coincidence. But not just that, we also were able to localize this. So Fermi said that, okay, this burst came from about this part of the sky, and it was the same part where LIGO and Virgo also localized the source. Now the sky is about 41,000 square degrees, and this was localized to order of 100 square degrees. So again, there is less than 100 actually. LIGO Virgo localization finally was much better than that.
That's good.
And that again means that the odds of these two things, if they were random, unrelated events, then both of them being in the
We
same
also were
part of
able
the
to
sky,
localize
the
this.
odds
So
are quite low.
Fermi
Again, 1 in
said
a
that,
thousand, which
okay, this
means that
burst
it
came
comes
from
down to
about this
about
part
1
of
in
the
a
sky,
million
and it was the
odds
same part
of
where LIGO and
these two
Virgo also
sources
localized the source.
happening at the
Now the
same
sky
place if
is
they were
about
not actually
41,000 square
related.
degrees, and
Okay,
this
so
was
let me repeat
localized to
that.
order of
If
100
there
square
was,
degrees.
if I
So
see
again,
this
there is
gravitational wave
less than
source,
100
and at the
actually.
same
LIGO Virgo
time
localization
and
finally
at the
was much
same
better than
place
that.
I see a X-ray
And that
source,
again means
then
that
there
the
is only
odds of
1 in a
these two
million
things, if
chance
they
that
were
there are
random,
two
unrelated
unrelated
events, then
sources
both of
that
them being
happen to
in the
pop up in
same
the same
part of
part
the
of the
sky,
sky
the
at
odds
the
are
same
quite
time.
low. Again, 1 in a thousand, which
That
means
is
that
good
it
enough
comes
odds
down to
for me.
about
Now
1 in a
let's
million
focus
odds
on the
of
afterglow. Okay,
these two
and the
sources
key part here is
happening
that
at
the
the same place
afterglow
if they were
was
not 41,000 square degrees,
actually
and
okay.
this
So
was
let me repeat.
localized to order of
Okay,
100
I've
square
I've
degrees.
gotten a
If I see
feedback
this
here that there is some
gravitational wave
sound
source
echo
and
that
at the
we are
same
getting, so I'm going
time
to pause for
and
a
at the
moment.
same place I see a X-ray source, then there is only 1 in a million chance that there are two unrelated sources
Both of
that
them being
happen to
in the
pop up in
same
the
part
same
of the
part of the
sky
sky.
the
At
odds
the
are
same
quite
time.
low.
Again, 1 in a thousand, which
That
means
is
that
good
it
enough
comes
odds
down to
for
about
me. Now
1 in a
let's
million
focus
odds
on the
of
afterglow. Okay,
these two
and the
sources
key part here is
happening
that
at
the
the same place
afterglow
if they were
was
not actually related.
actually
And
okay.
this
So
was
let me repeat
localized
that.
to order of
Okay,
100
I've
square degrees.
so this
If I
afterglow
see
that we saw was like nothing else we have ever seen before. Okay, and this afterglow basically was we know a lot of different explosions in the sky like supernovae, novae, flare stars, but this was not like anything we have ever seen before. And not just that, if it is something weird, that is good, but that is not good enough. What was also important was that this afterglow matched theoretical expectations that we had, and that put together again convinced us that this optical and infrared source which we had found, which was also then studied in radio and other wavelengths, was indeed related to the gravitational wave source. Okay, so based on all of this, we were sure that it was the same event, and that is how we drew a lot of conclusions. And really, I want to highlight again here that it was important that it was not just some weird new creature we had seen, it was the kind of creature that we expected to see based on theoretical modeling. So we knew that it should have a certain kind of profile, how the brightness should change with time, what the spectra should look like, and all of those matched our expectations when we actually observed them. So, by doing all of this, what is it that we finally learned? Well, let's go back to the two main questions that I had asked. The first was R process element. So, slightly complicated graph here, but bear with me. What is plotted on the x-axis is what is called the atomic mass number. That's the total number of protons plus neutrons in the nucleus of an atom. So you have lighter elements here that would be called the first peak in nucleosynthesis. The second peak, those of you who've studied these things, this is where the lanthanide series, that is one of those rows under the periodic table, comes in. And then there's the third peak. It was postulated that the second peak and the third peak are largely formed in mergers of neutron stars. Okay, so most of these elements where you see around the universe, including a lot of these lanthanides, were all formed in the merger of neutron stars, and that can happen. Um, that is what the prediction of theory is. But then we actually went and observed these. Here are a few spectra which are plotted. They might look completely like gibberish to you, but in trained hands, these mean a lot. The shape of this entire thing and all these little bumps and wiggles in between mean a lot to us. We went and observed this even 4-6 months later. We are still continuing to observe this source with radio. And if we take all of that data, we can actually calculate that it is exactly what you would expect to see if all of these elements over here were synthesized, because these elements, when they are just newly formed there, a lot of them are radioactive and they decay with time, and that creates a predictable energy release there, and we can actually observe all of that. Think of it very loosely speaking like a bomb, a nuclear bomb that is exploding for 6 months. Okay, and we see how the explosion is progressing, and that is what allowed us to conclude this. The other question that I had asked was the equation of state. So the equation of state, or EOS, is described in loose terms as soft or stiff. So by soft or stiff, what I mean is you try changing the pressure. Okay, so if I have some matter and I increase the pressure, if it gets compressed a lot, its density will change a lot, and that is called a soft equation of state. On the other hand, if it is not very compressible, if it is stiff, then the density hardly changes, and that is called a stiff equation of state. So what we already knew before this event was that certain very heavy neutron stars exist, which means that the equation of state cannot be very soft. But what we learned from this is that the equation of state actually cannot be very hard either. So this is parameterization. I won't go into details of this, but you can go and read this paper online. It's on the a preprint server called the Archive. And based on analysis of the gravitational wave signal, we could conclude that the equation of state is not too hard. It is in the softer regime. The very soft region in this corner has already been ruled out by other observations. So all of this now happened with just one detection. But then LIGO in 2018 underwent a series of upgrades, and in 2019 started another observing run called O3, the third observing run. And LIGO and Virgo together detected a lot of different candidates. This is science that you can witness as it is happening. There are apps you can install on your Android phones or iPhones, which will actually allow you to get alerts when any of these events is detected. We'll come back to this in the last slide again. And some of these events, early alerts were sent, but then they were retracted because more analysis showed that this was actually a noise spike. But from all of these events, and the list of these events is available at this URL. You can come back to this video later and note down these URLs. We will also post some of them in the comments and content below. Of all of these, let's focus on one in particular, an event called S190425Z. S stands for super event. That's just some internal nomenclature. This is an event that happened on 25th of April 2019. So just less than a year ago. Now, this particular event, based on the gravitational wave detection, this is an all sky map. Think of it like an atlas for Earth, but plotted for the sky instead. And orange regions are where the merger is likely to have happened. So the 90% area, there's 90% chance that it is contained inside these lines that you see here. And that area is about 7,500 square degrees. That might not mean much to you intuitively, but if you have ever gone and looked out at the night sky, and if you have identified something called the Big Dipper or the Great Bear or Saptarshi, then you see that shape, and if you put a box around it, that's about 250 square degrees. For comparison, the full moon is about a quarter square degree, and a typical telescope can observe about 0.1 square degree of the sky, and can take up to 100 images per night. Okay, there's differences across telescopes. So 7,000 square degrees is a lot. If we wanted to use something like HCT to study this, we would have to spend close to 750 nights or 3 years just to image this entire place. That is extremely difficult. The second thing is that this was about 500 million light years away from us. Okay, so you can see these distance plots over here, and that means it is about 4 times further away. Now, light follows what is called an inverse square law, which means that if a source is twice as far away, then it appears 4 times fainter, 2 squared. This one is about 4 times as far away, so it will be about 16 times fainter, which means that it's going to be much, much harder to detect. And that is indeed what happened. So we extensively searched for this. We were among the groups that was doing this search, many other groups around the world as well. But unfortunately, we did not find anything there. There was no counterpart found. The story is same with all the other events that you saw. And so far, GW 170817, the first event, the first binary neutron star merger that was detected, is still the only event for which gravitational waves and light have both been detected. So now I should tell you how exactly do we search for these, and I'm going to focus on two particular instruments. Okay, so the first one is, of course, to do a search. The most important thing is the team. So here's our team of cosmic detectives. The first photo shows some members. This is when we were studying 170817. A lot of these people are now all over the world working in different groups across Japan, Europe, US, and so on. And at the bottom, you see our international collaboration called Growth. We actually make sure that observatories all around the globe are collaborating and working together to do this. Growth itself is an international collaboration, not because we don't have enough resources here. So here's a map of all the professional telescopes in India, and there's a bunch of telescopes in Nainital and at a site near Nainital called Devastal. We have some at Mount Abu. There's Ayuka Giravli Observatory right next to GMRT. Several telescopes at Kavalur between Bangalore and Chennai. And then up here we have the Growth India telescope and the Himalayan Chandra telescope. AstroSat is not in Afghanistan. It's a space telescope, but I didn't know where to put it on this plot. And the green ones again are radio telescopes in the country. So we have a lot of these. But what if there's an event when it is daytime in India? All of these optical telescopes can't do anything. So we really need collaborations around the world. And that is where a network like Growth comes in. So Growth is an acronym for Global Relay of Observatories Watching Transients Happen. So if you think that SHIELD or Hydra were the most complicated acronyms ever invented, no, we beat those by far. We have a set of telescopes all over the world. We have partners in 8 different countries, by now more than 17 partners, and you can find details on the Growth website. And as a part of this, we also have set up a fully robotic telescope in Hanle, where you saw a time-lapse video of that right at the start. So this is a telescope that has a 70 centimeter aperture, and it has a very, very sensitive camera. State of the art camera. This is about 16 megapixels. You might say that my phone has a lot more megapixels than that, but your phone has far, far lower sensitivity than that. Okay, so this costs about 1,000 times more than the camera, than your phone itself, probably. But this is an extremely sensitive telescope. We can get very good measurements and observations with that. Here's a picture of the site, this time in daytime. This is the dome. Beautiful Ladakh mountains in the backdrop. A site definitely worth visiting. Again, those of you who are planning to go there, it seems that anyone who buys a new motorcycle, autopilot automatically ends up going there. The observatory is open. You can actually contact us beforehand and arrange for it so that you can actually go and see the telescopes. Here's one of the still frames from that beautiful Milky Way in the backdrop. And here's what the telescope and the dome themselves look like. This is the telescope. The camera is, this is the eyepiece mounted here. Camera would be on the other side. And all of these pictures were taken during commissioning. Now the question is, how can we do better? Okay, so we had detected this, but we missed a lot of events that came later. So going forward, if one event has given us so much information, I told you about that one paper which had 3,500 authors, but even now, more than 2 years since the event, we are still seeing that people are almost publishing one new paper per day. There are more than 850 scientific results published based on that one detection alone. So how can we do better? We clearly want to detect more of these. Well, you always start with lessons that you learned from your first observations. So here I'm focusing on what we need with X-ray and gamma ray space telescopes. So we need an order of magnitude more sensitivity, which means you want telescopes which have a much larger collecting area so that you get more light, you collect more photons, you want lower noise, you want better background rejection. You also want a very broadband spectrum. You don't know exactly what is the nature of light emitted from this. So you want to be able to detect low energy X-rays, high energy X-rays, gamma rays. Now all of these are blocked by the atmosphere. That is great news for us, because otherwise the high energy radiation from the sun would have completely sterilized the Earth. All of our DNA would have broken up. and life would never have formed on Earth in the first place. But if you are X-ray and gamma ray astronomers, that atmosphere means that you can't actually do any of these studies from the ground. So you have to take up a telescope, go to space, and observe from space. The third is that you don't want to have a scenario like AstroSat again, where you had a telescope that was extremely sensitive. It could have easily detected this event, but the event happened behind Earth, as seen from AstroSat. In order to get continuous all sky coverage, you actually want two telescopes on opposite sides of Earth so that you can cover the sky. With these ideas in mind, we actually have gone ahead and proposed a mission called Daksha. So Daksha is going to be a set of two satellites. This is a completely Indian mission built by several institutes around the country. This is still in proposal state. I'll get back to this later. But these two satellites together will provide much, much higher sensitivity than any existing space telescopes for detecting these kind of explosions. So what we will have is three different technologies, three types of detectors that will observe the sky in low energy X-rays, medium energy X-rays, and in high energy gamma rays or high energy X-rays. These detectors, the medium energy X-rays, incidentally, are the type of X-rays that you colloquially refer to. So if you are looking at an X-ray scanner at a railway station or at an airport, or if you are looking at X-rays which are used in a hospital, all of those usually fall in these energy ranges. So when I say Daksha is going to be better than others, these are the current record holders for detecting gamma ray bursts. There is the Neil Gehrels Swift Observatory by NASA, and there's a NASA plus ESA mission called Fermi. Um, these are the currently active space telescopes, but even these were not sensitive enough to find those new bursts, which happened in '03. They did not detect anything. So we now are talking about building something better, and not just better. We are talking about something that will be 5 to 10 times more sensitive than the state-of-the-art instrument, and all of that will be built right here in India. So, what is the advantage that Daksha will bring to the field? We will be far more sensitive than current satellites, which means that we expect to detect far more high energy counterparts than any of these to these sources than have been detected so far. Current detections sit at one source. We expect to detect a few dozen sources every year. Not only that, we will detect more gamma ray bursts than ever. Based on our calculations, Daksha will detect as many gamma ray bursts in just 1 year that all past satellites put together have detected in the last 20 to 30 years. That's how much more sensitive we will be. And also, there's a lot of other science that we can do. We can study X-ray polarization, we can do Compton imaging, a lot of details for this. And that is why this very, very ambitious mission has been proposed by us. What is the current status? Well, we proposed this mission to ISRO. They liked the plan, so they have given us some seed funding to show that this actually is feasible. It's very easy to stand up and make claims, but it is not science if you can't prove it. So we have to prove that we can actually do all of this and that we can do it correctly. And based on that seed funding, we are now doing research and development to develop a proof of concept. Many partner institutes here. IIT-Bombay is leading this with a lot of support from PRL Ahmedabad, TIFR Mumbai, Raman Research Institute in Bangalore, IUCA in Pune, the UR Rao Satellite Center also in Bangalore, and so on. So a lot is happening on this, and if things go well, the mission will get approved and we will launch in a few years. So all I can say is stay tuned for updates. With this, let's get back to the main topic of today, which is gravitational waves and their counterparts. Here's a status update about the gravitational wave observatories itself. I talked about O3 and I showed you this large list of neutron star candidates. There are also several dozen black hole candidates that have been discovered by LIGO. And all of that observing was going on, but now because of the COVID-19 situation around the world, the gravitational wave observatories actually have suspended the current observing run. We are evaluating the situation and we will determine on the basis of everything whether we want to resume observing or not, or we could actually take a commissioning break, improve the sensitivity of the observatories, and then start gravitational wave observations again. So this run was supposed to go on until the end of April, but we have stopped the observing on 27th of March. So when I told you that you can install an app that will give you latest gravitational wave event updates, That app is still working, but because of the situation for which we are doing this web lectures at all, the reason why you are all sitting at home, the same reason, the safety of all of our team working there is what we kept at the forefront, and we have suspended observations with LIGO right now. So that is all I have for today. We have purposely kept the lecture to about 45 minutes. That gives us a lot of time for question and answers. For more details, you can visit the LIGO India website, or you can visit the IUCA webpage, gw.iuca.in. You should, of course, connect with us on social media. I will leave this here. This YouTube channel is our newest addition, but other than that, we have presence on Facebook, on Instagram, on Twitter, and that is where you will get to hear all the latest news from us. For students among you, this is also where you will get to hear about internship opportunities and other projects. Sometimes we will also advertise other positions through these channels. So if you are interested in gravitational waves, these are the places that you should follow. Okay, so I have here with me some questions which were asked through the talk, and I'm going to go through them one by one. So the first question that I'll answer is from Divyanshu Tiwari. Does the first generation of stars produce neutron stars? That's a very good question. The first generation of stars, um, which funnily enough are called population 3 stars. Population 1 are the newest stars in the universe. Population 2 is older ones. Population 3 is the first stars. And Divyanshu asks if those stars produce neutron stars. To the best of my knowledge, no. The evolution of those stars proceeds in such a way that they will explode as supernovae, leaving behind only black holes. You need the star core to be of a certain mass and have a certain kind of composition to produce neutron stars, and that those conditions are not met by the so-called top 3 stars. So most likely they will have died off in supernova explosions, leaving behind just black holes, not neutron stars of any kind. The next question is from Parth Bhagwat. Do gravitational waves interfere, and if yes, can LIGO differentiate? That answer, the first technical answer to your question is yes, gravitational waves can interfere. But before I go into whether LIGO can differentiate, you know very well that light can interfere. You know that sound can interfere. Can your eyes and ears distinguish between light coming from different sources? Yes. Because to get interference, you have certain conditions that need to be matched. You need the source to be coherent to begin with. The source has to emit coherent waves. If you have two different sources emitting coherent waves, then interference could be possible. Gravitational waves, gravity is an extremely weak force. Okay, so for instance, I have my phone in my hand here, and just the very fact that I'm holding up this phone shows you how weak gravity is. Why? Because I have my little hand here, maybe just two fingers holding up this phone, and all of Earth, 6 into 10 raised to 24 kilograms of Earth, is trying to pull this down. And my little finger here can actually oppose that. Right? So gravity is very, very weak, and gravitational waves are also extremely weak. And what that means is there are very, very few sources. Okay, even the odds of having two detectably bright sources active at the same time are very low. So in reality, do we expect to see interference of gravitational waves with LIGO? Not really. So observationally, that scenario will not arise. Next, we have a good question from Nishant Pawar. Nishant asks, how do we differentiate between the gravitational wave signals from black holes or neutron stars or any other sources? So for this, let me actually go back to one of my older slides, which is this one. Oh, not this, actually this one. Okay, so let me pause this movie in between. So, or let me go to the next one here. Okay, so here what I've shown is as these two black holes are orbiting around each other, and as they come closer, you see that the gravitational wave amplitude follows a very particular pattern. Okay, and if you now look at the pattern for this system of binary black holes which merged, okay, keep this pattern in mind, and then let me go forward to the next merger, and you can see that now the nature of that pattern was quite different. Okay, so this one was weaker, but also the first frequency was lower, and so on.
So this is called the chirp waveform. Another way of looking at the chirp waveform is in another of my slides here. So if we go to 170817, okay, here is the frequency as a function of time. We had spent some time on this slide. The way this changes is very different for black holes and neutron stars. Okay, first is if you see a gravitational wave signal whose frequency and amplitude are both increasing with time, that's called a chirp. And a chirp is a classic signal of two objects spiraling around each other and merging. And you can actually do this analysis. There's also a nice paper on arXiv. Look up a paper by Jasjit Singh Bagla and collaborators. If you have done first year BSc physics, you know enough science to be able to actually calculate and verify this by yourself. Okay, so this chirp waveform, you can actually show that it is coming from only neutron stars and black holes are possible sources. If you have black holes, then the chirp waveform does not last for this long and it doesn't go to these high frequencies. It would be cut off much earlier before that, and it would also have a different shape. So based on the nature of the waveform, we can actually tell whether it is black holes or neutron stars. We can basically tell the masses of the source, and we can also tell how far away they were. So all of this comes from analysis of the waveforms. Shobhit Ranjan asks, how long did the optical and radio afterglow remain? The optical afterglow of this source was seen for a couple of months. After that, the source went too close to the sun, which means that we couldn't observe it with ground-based telescopes anymore, or even space telescope. No telescope wants to point too close to the sun. It's way too bright. Several months later, when it came back from behind the sun, we were still able to detect it with infrared, the Spitzer Space Telescope. Radio afterglow, on the other hand, it took many days to become bright in the first place. Radio afterglows are like that. Even X-rays, by the way, there was this initial gamma ray peak which you are seeing here, but these peaks which you see, but you can see that the radiation immediately fell back to basic levels that you expect from the entire sky. And then it took about 10 or 15 days for the X-ray source to become bright again. Radio in itself actually brightened almost a year after the burst, and since then it has been fading. It is still visible in radio. So the afterglow lasted for a very long time. Abhishek Khandelwal asks, why were there two regions for GW 190425 to locate the sources? Why were there two blobs? So let me go to that map. Okay, I think that would be somewhere here. So you can see that there is one blob here, and there are actually two blobs that you can see here. So the way this localization is done is that you have multiple detectors detecting these waves, and you try to match the pattern. So suppose this is Earth, and there is a gravitational wave source over here. As the signal travels, it will be incident on this part of Earth before, and then this part. So a detector here will see it slightly before a detector here. Okay, and based on that, you can actually say, okay, the source was somewhere there. Now, if you have only two detectors, say one over here and one over here, then you can only calculate the angle. You can figure out, you can't differentiate between a source that was above or below because the delay would be the same. Actually, you get a ring on the sky. So this is the kind of ring that you would expect. Remember, this is a map projection. If I had actually drawn this on a sphere, it would be more obvious that this really is the ring. And that ring is how you figure out where the source is. You break the ring based on the sensitivity of your two detectors, or if it is actually detected by a third detector. So this one was, oh, I've not included that column here. I don't remember if it was detected by two detectors or all three. But based on which part of the sky your detector is sensitive to. So basically, if the source was here, one of the LIGO detectors has no sensitivity here. And based on that, you can rule out this location. Now, where there are two parts of two rings parallel to each other here, or you see something similar here as well. And that again has to do with that repeating nature of the waveform. So let me do this. So my waveform looks like this. So suppose I detect this in one detector, and if I detect a slightly delayed waveform in another detector, now you have to see whether these two peaks were to be matched to each other, or whether these two were to be matched to each other. And those would have given you, one of them would correspond to this ring and the other would correspond to this ring. So based on these matching, there is some ambiguity in that, and that can give you these blobs on the sky. So good question. I'm not sure if you got a satisfactory enough answer, because you do need to go into a little bit more technical detail. But as follow up, if you send that question to us, we can point you to more detailed resources. After that, there is Debolina Chatterjee asking what's solar R process abundance. That is uh, the abundance of R, the relative abundance of R process elements as compared to hydrogen. And solar means the amount of those elements that you see in the sun, or broadly speaking, in the solar system. So you are saying that how many of these atoms should there be if the sun is really the standard for everything? We have another question from Yuvraj Murli. Will the Betelgeuse supernova help in the better analysis of gravitational waves and element formation? Very good question, but I have to answer something else first. So far, I have been talking of only one type of gravitational wave sources, which is these compact binary mergers and their inspirals. Um, but other than that, there are also other types of gravitational wave sources. So if a star explodes as a supernova, there's a lot of mass moving in a very, very short amount of time. And that could also give you gravitational wave emission. If you have neutron stars which have any slight asymmetry, those could be what are called continuous gravitational wave sources. And of course, the universe, we have not finished all of science. The universe could also always throw us a surprise, and there might be completely unexpected sources of gravitational waves. Now, supernova gravitational waves are expected to be far, far weaker. So while these sources we saw were millions, hundreds of millions of light years away, we can see only up to thousands of light years away, or tens of thousands of light years away, if we are looking at supernovae. And for that reason, Betelgeuse would be an ideal candidate. Betelgeuse is about to explode soon on an astronomical timescale. It might be a million years from now before that supernova explosion happens. So I would not wait for it. But if Betelgeuse does really explode as a supernova, yes, we will get to learn a lot more about a lot of different aspects of physics, including nucleosynthesis of elements, stellar structure and evolution, gravitational waves, formation of compact objects, and so on. It would be amazing treasure trove of discoveries for astrophysics. Okay, so I will now take the last question, which many of you have asked. So I won't name anyone in particular, which is what might be the future research opportunities in this topic? And there are many, many, many answers to this question. Okay, so to answer this first, I'm going to come back to this slide, because this is where you can actually send us questions if there are any other questions that are still unanswered. We will try to, we get a lot of questions, we'll try to get back to you. We will try to answer all good questions that you have. Also, the opportunities that we have will all be announced here. If you are looking at specific opportunities to get involved, well, there are some 12 or so, I forget the exact number, several institutes across the country, including IUCA, TIFR, ISC, ICTS, IUCA, DCSEM, RRCAT, IPR. All of these places are working on gravitational wave physics. Many of them are part of the LIGO scientific collaboration, and all of these places do have undergraduate programs, PhD programs. So students can actually apply there and join. This is not limited to just physics or astrophysics students. There are lots of opportunities for engineers as well. This year, a lot of internship programs have been cancelled because of the COVID-19 situation. We really urge you all to follow all the instructions given. Please stay at home, stay safe, do not break social distancing norms. But under normal circumstances, we have internship programs that people can participate in. and students can apply for those. There are also some citizen science projects that come up. Gravity Spy or blip detection is one of them. So there are programs that you could participate in and just give some few minutes a day if you want, or few hours a day if you're really enthusiastic, and help with gravitational wave research. So there really are opportunities that are available across the spectrum, and you can participate in any of those. Uh, by the way, there's one more clarification based on some inputs on some comments we have seen so far. I did say that we suspended O3 1 month or more before planned. That does not mean that we are losing a lot of science. Of course, we would have liked to observe more, but as the situation normalizes, based on how quickly things change, we may start O3 again, or we may say that, okay, we wanted. So the 1 year observing period was picked as a convenient number. 12 instead of 12, if we do 11 months of observing, that's okay. We get about 8%, 9% less data, but we have still gotten a lot of data, a lot of great science coming from it, and we were scheduled to shut down for upgrades anyway. So the collaboration will evaluate this and may decide that it is time to go for updates. Lot of interesting observations have already been made through O3, and all the LIGO team that is sitting together right now. By together, I mean virtually together, sitting at their homes right now, are all working very, very hard on this data analysis. So a lot of papers and publications are expected to come from this. Um, I will end with that. Thank you all again for joining us today. We will circulate some feedback requests, and we would really like to hear from you. We are very happy with the response that we have received so far, and we hope that we um, give you a positive outlook and some positive things to focus on as we all stay home, stay safe. Thank you all. Good day. Bye.